Right? I'm really excited to be here to see all you guys, and hopefully this will be an understandable talk. I'm not trying to make it like super cerebral or anything, but just something that hopefully will help everybody to understand how to talk about science and faith with people that you run into. So this is a beautiful picture of the Milky Way. You probably can't see this in Atlanta that often because at night there's lots of city lights, right? You got to go way out to someplace like Waycross, Georgia, if you're going to see something like this. But if you sit there and you look for hours, the stars start to come in, and then it's really beautiful. And this is what I want to talk about, the structure of this. This is not random, and this, I would argue, points toward a God. So, yes, I teach physics, but that's not me. This is a blackboard, and there's lots and lots of equations here, and there's lots of stuff. And most people, when I say, like at a family reunion, they say, hey, what do you do? And I go, I teach physics. They go like this. They back off. They go, this is really horrible. Most people don't like physics, okay? So I understand that, and I'm a little insecure about it. So you got to help me, okay? All right, so what I'm going to say is, first of all, let's just see if we get to know each other. Does anybody know what these are? Equations, yeah? Maxwell's a holy cow. How do you know that? Awesome. We're gonna have to talk afterwards. Now, let me. What's your name? What's your name? Alexa. Alexa. What do you feel when you see these equations? Love. Okay, appreciation. Right. I agree. Okay, so one thing I can say about this is when you put all these equations together, they talk about electricity and magnetism, and what they do is they allow light to travel through space. These equations allow light to just exist. And this is a way of describing what light is. But there's another way, right? Jesus also says, I am the light of the world. And that's a different kind of light. And so science answers our questions about, what is light? How does it travel? What's its speed? How does it reflect? And all those kinds of things. But there's other things I'm curious about too, which is, why am I here? What's the purpose in my life? How should I treat other people? Is there life after death? Or is it all just a bunch of molecules banging together, and then at the end we die? And is everything moved by just evolution? Is that all there is to it? And oftentimes when people get entranced by these, and I know you're tempted, this is beautiful, to go down this hole and just think science is all there ever is. One of the problems of that view is that it doesn't leave a whole lot of room for things that we can't evaluate with the scientific method. It doesn't leave room for things like, what is meaningful in life? What is valuable in life? Why am I here? What is our purpose? And I would argue that a complete life actually should bring in both this and this. So yes, everyone should know Maxwell's equation, but definitely everyone should know Jesus, okay? So what I'm gonna do is go over a couple arguments that might be helpful, either in you thinking about science and faith, or in you talking to friends about science. And this is really gonna have to do with the structure of the universe, the laws of physics, the Big Bang, and how that might relate to questions of God. And so I'm going to talk about something called the cosmological argument. We're going to talk about how everything got here. And I would argue that this points toward a God. The other thing we'll talk about here is the teleological argument. This talks about the purpose of the universe, which I think we can understand by the laws of physics. And I'll explain that a little bit more. They're just amazingly fine-tuned to allow life. That's what this will be. And then at the end, we'll talk a little bit about this. Conclusions. Okay, the cosmological argument. So what does the Bible say about how everything got here? It says there was a creation. In the beginning, God created the heavens and the earth, and God said, let there be light, and there was light. And right when he said that, Maxwell's equation was up in the okay? So it says there was a creation. But now if you sit back and you think about it for a minute, it didn't necessarily have to be that. In fact, many people thought that the universe just has always existed. And it didn't come into being at all. That it just always was. Okay, but the Bible has a very definite stance on this. It says there was a beginning. There was something that started. And the person who started it, or the being who started it, was God. So let's see, is there any evidence for this kind of thing? Can we look into science and see if that statement, very early on in the Bible, at the very beginning, has any scientific evidence that backs it up? So let's talk about this. So here is another view of the Milky Way. And so that's a clump of stars right like this. So probably most everybody knows we're in a galaxy. It's some disc-shaped thing. And we're in the middle of that. And the only way we can kind of see it is if we look in toward the center. And if we look toward the center of the Milky Way, we see the edge. So this is like a giant disc, or maybe a waffle. We just ate at Waffle House. So it's like kind of waffle, and you're looking into the middle of it. And out here are other stars as well. But this thing is pretty big. And so here's a nearby galaxy. This is Andromeda. So now somebody like Max, you probably know. I'm gonna tell you to be quiet. But let's just talk about how big this thing is. Maybe somebody knows, but what if I was over here and I shined a flashlight or a laser pointer and I let the light go all the way across the diameter of this galaxy and somebody over here was waiting for it? How long would it take that beam of light to go across this galaxy? Would it take a year? It's 100,000 years to go from this end to that end. It would take 100,000 years to go across the galaxy. These things are extremely big, okay? But that's just one. How many galaxies do we have? I recently asked an astronomy professor who gives a lecture right before me. He's figuring out, wait, before you go, how many galaxies do we have? And he goes, right now, the estimate is it could possibly be an infinite number of galaxies, and this is just sort of one that's like our galaxy, 100,000 light years across. That's just incredible. So it's hard to believe all of this stuff. It's incredibly vast. So how did it get here? Now, here's an atheist philosopher, Bertrand Russell, and this is the opinion that I told you about a little bit before, is he said, well, the universe has always existed. That's Bertrand Russell. And this was the view of Aristotle, who was the great Greek philosopher that most scholastics believed in and thought was the authority on everything. And so throughout almost all the Middle Ages, people thought, well, that's a view that scientists hold, that the universe has always existed. And yet the theological view, the one by the monks, said that no, the Bible says that there was a creation. Here's another person, also a guy with a pipe. He currently had to smoke a pipe in those days. And this is Edwin Hubble. You've probably heard of him because the Hubble Space Telescope is named after him. What's his deal? So one of the things he did is he got a hold of a very large telescope, and he was able to look far out. And what they saw for the first time was basically these little tiny dots that we now know are galaxies. They didn't know quite what they were because when they had smaller telescopes, they looked like stars, but they were slightly smudged. Like, what is that? Why doesn't it look like just a point? Why is it smudged? And then when they got a much more powerful galaxy, a much more powerful telescope, they were able to see the details of the galaxy. And what they wondered about for quite a while was, are these just funny shaped stars that are kind of, near us, or are they island universes? Are they really, really big, like 100,000 light years across, but then super, super far away? They didn't know what that was. And his work began to unravel this. And one of the things that they began to find was these are indeed galaxies are island universes. They're enormous. They're not just stars. And here's the other thing. Galaxies are receding from us. They're moving away from us very, very rapidly. How did they know that? They knew that. Well, this is just a picture of the idea. So imagine space is just sort of like a balloon. And on this balloon, I'll draw lots of little dots, and each dot represents a galaxy. Now, as I blow up the balloon, each one of those dots is going to get further and further away from itself, from other nearby dots, right? And so they're moving away. So if you're standing on one of these galaxies, what you would see nearby is everything just moving away from you. You'd think, what happened? Why did everyone not like me? But they're just moving away from you, right? Because what? Space is expanding. Space itself is expanding. So let's just say we did this. Say I had a little button here, and I could press this, and it would cause everything in the room to be twice as big. What would happen? The desk would be twice as big, you'd be twice as big, but the distance between your nose and your friend's nose would grow to be twice the size. So you look at everyone around you, and they basically be moving away from you very rapidly if I press that button down. So if space itself is expanding, the galaxies are moving away. That's going to tell us something about how this all started. So let's just ask, how do we know the galaxies are moving away? How did he know? He didn't look at the galaxy and just go, wow, I'm watching it for 5 minutes and it looks like it's moving away. You can't do that because the distances are so huge. One of the ways of finding out whether a galaxy is moving away or not is by looking at this thing. If this kind of stuff bores you or bothers you, then you can tune out for a minute or two. It'll wake you up in a minute. All right, so this stuff, Gabby, you probably know all about this, right? Spectral lines. Yeah, she does. She does. Okay, so what happens is, here's basically a rainbow of colors. This is the visible spectrum of light. And what you have in here is light is being emitted by a star. So light is shining and it's going through space. But then between where we observe it with the telescope and where that star is, there could be a big gas cloud of hydrogen. And as the light goes through the hydrogen, what happens is it's absorbed in a particular way. So because of the atomic structure of hydrogen, it can only absorb certain wavelengths of light because they have certain particular energies. And so what happens is if you shine light through a hydrogen gas cloud, what you'll find are little lines like that. And what that means is that that line has light of a particular wavelength that hydrogen gas cloud absorbs. You don't need to know all the details of it, but it absorbs that. Now here's where this becomes interesting. That's if a galaxy is not moving at all. When you're just looking at it, we'd see those spectral lines, just as if we were doing a desktop experiment shining a flashlight through an orb of hydrogen. We'd have the same lines. But what happens if it moves? If it moves, these lines shift, okay? So if the galaxy is coming toward you, what happens is these lines move a little bit toward the blue end of the spectrum. See how they're different. And if the galaxy is moving away from you, they move toward the red end of the spectrum. Why do they do that? Okay, now I'm going to make some noise with you. Okay, so we come from Indianapolis. When you go to live in Indy, you must go to the Indy 500. And the first time you go there, you realize it is incredibly loud. And the cars come at you and they go, you hear the difference as they come at you, it's high pitched. So as they're coming at you, the frequency is high. As they go away from you, the frequency is lower. The sound waves change coming at you. So the sound waves are coming like this, okay? And if the car's coming at you, it's going like this, and the waves are being pushed by the car and they're coming at you. If I'm going away and I'm going like this, the waves are stretched out longer. And so they're of a lower pitch. So just as you can hear pitches, high pitch in light, or high pitch in sound, and low pitch in sound, you can have a high pitch light waves and a low pitched light wave. Low pitch is red, high pitch is blue. Okay, so blue and violet are higher energy, they're higher frequency. Red is lower energy and lower frequency. So if you're going to get damaged, you're going to get damaged by the ultraviolet rays that are really energetic. Infrared is not damaging to you. Infrared just comes off by heat, so it's not damaging at all. So you can have a shift in light rays or these spectral lines based on whether this galaxy is coming at you or moving away from you. Does this make sense? Yes, okay. Yeah. And then the other thing is the size of the shift can tell you how fast it's going. So Hubble was able to take his telescope, look at these things and go, wait a minute, they're island universes, they're galaxies, and some of them are moving away incredibly fast, but they're almost all moving away from us. What does that say? What does that tell us? Okay, yeah, they sound like race car. I'm not going to do the sound again, even if you ask me. I'm not going to, no. Okay, so now here's that explosion, right? So they're all moving away. So you can imagine us being, I don't know, right here, and you see all these galaxies moving away from us. But that's true for every galaxy, right? So what happens if I run this in reverse? Here's my little animation. Boop, boop, boop. Okay, if I run it, if they're all coming away from each other, that means they all had to be closer to each other at an earlier time. Right? We go back in time, back in time, back in time. And what do we get? We get the entire universe. Remember how big each galaxy is. The entire thing, 30+ billion light years across, is now compressed into something the size of a beach ball, possibly smaller. All matter in the entire universe is compressed into something the size of a beach ball. I cannot emphasize how incredibly stinking crazy, right? What the heck? And when you get things that small, the laws of physics don't even work anymore, right? Gravity is so powerful, all sorts of things are just messed up, all right? So the laws of physics break down, and we no longer have, I mean, I can't teach that. No one can teach that level. Physics is gone, all right? But here's what we know. Everything that came into being started out from that little cosmic orb, if you will, and then it expanded, right? So that explosion had to have a beginning, right? This was an event where all things, including space itself and time, this gets into Einstein's general relativity, but space and time are intertwined together with matter and energy. All these things are together. And so everything kind of had to just start at that moment. Wow. All right, so this leads to some questions. First of all, how did these guys react to it? When Einstein wrote up his equations, he didn't know what the solution was. He wrote up these equations of general relativity. It took a few years for people to go, okay, there's different ways these equations could be solved. One of them was that basically everything would expand like this. And he goes, nah, that's not, nah, that can't be. Until Hubble, the guy with the pipe, started coming up with all the information about the galaxies moving away from each other. And he hated it. He's like, I don't like it. No. Let me add a constant to my equations that offset that expansion so everything will cancel out so we won't have this beginning of time stuff. Einstein didn't want it. Was he alone? No. There were other people. Here's a pouty picture of Einstein, just so somebody didn't want it to happen, okay? But what about other people? Okay. Other people, let's see. Okay. To avoid this beginning, Fred Hoyle and colleagues proposed that matter was continuously created at the center of the universe. Let's not have a Big Bang or something. In fact, the term Big Bang was invented by Fred Hoyle as a joke to try to make fun of this idea that everything started out from the size of the universe, which our evidence now overwhelmingly points to. All right, but Fred Hoyle said, no. Somewhere in the center of the universe, there's like a faucet, and it's creating matter, and it's just continuously spilling out all the time. That was his solution. It's called the steady state universe. But he tried to wiggle out of it. He wasn't the only one. Almost every scientist at the time avoided this idea. They felt it to be reprehensible, disgusting. These are not words I'm adding. These are words that you can get from them. They hated it. Okay, so this is Fred Hoyle. That's what he looks like. It looks like what? Oh, yeah, a little bit, yeah. We should have a movie and ask Matt Damon to play him. Yeah. Right? So almost all of them disliked it. Here's my other pouty picture, I think. There we go. Okay. So why did they dislike this? Why did they not? And this dislike actually extended even until the 1990s, when a guy named John Maddox, who was the editor of Nature magazine. I don't know if you know about Nature. Nature's like the highest scientific journal that you can publish in, and lots of people want to publish in Nature. Maddox came out with a public editorial in the 1990s, basically saying the Big Bang is garbage. It smells like a theological position. We should shoot it down. This is terrible. It's going to make us all into theologists. We should not believe in this sort of stuff. I thought you were a scientist, guy. Let the evidence lead you where to go. Don't come out and I can lead you. I can give you a copy of this. He was the editor of the scientific journal Nature. This is incredible bias, right? Just wanting to shoot it down, wanting to just get rid of it. Okay? Scientists didn't like it because it pointed toward God. That's why they didn't like it. Okay? Now it is accepted that it was a beginning to time. Time had to start somewhere. All things were created. They haven't just been around forever. Okay? What or who began? This leads to a question that they didn't want to even admit was there. That's why they wanted to avoid it, because it's just so easily pointing to God. So here's the argument, cosmological argument. This is the formal view of it. Whatever begins to exist has to have a cause. So anything we see that comes into being has a cause. The universe definitely began to exist. That's what I just spent time telling you, is we have the scientific evidence for that. That's irrefutable, right? Therefore, the universe has a cause. And now I want you to think for a minute about what the properties of this thing is. This thing that caused the universe. What did it have to do? What was it like? I mean, what takes a little beach ball and then blows it up into perhaps an infinite number of galaxies, billions of light years across, with huge amounts of mass and energy? What kind of thing does that? Well, first of all, we know it had to be powerful, right? You can't just take something like that and make it blow up 30 billion light years across unless it's extremely powerful. What else do we know about it? It stood outside of time, because time itself was wrapped up in that space-time beach ball that we were talking about. Whatever caused it had to be outside of it, prior to it, or ontologically before it. I don't know what you want to say, right? It's hard to think about, but this thing wasn't in time. Okay? What else do we know about it? It was outside of space. All space was right in here. Right? All space was in this tiny little thing. Whatever this thing was, it was incredibly powerful. It was outside of time, and it was outside of space. What else? There's one more thing about it. It was a material. It wasn't made up of matter. Because all matter was in that beach ball that was initiated by this thing. It was an immaterial, extremely powerful, outside of time, and it also led to order. We'll get to that later. But when you start looking at these things, this is not too far from the traditional conception of God being omnipotent. This is him being eternal. Okay. This is he's omnipresent. Okay. And this is he's spiritual. He's not a material thing. Right. So these traditional concepts of God that have been debated and talked about by philosophers for centuries now found scientific evidence that pointed in that direction. I wouldn't say that this proves that there's a God. There's lots of people who debate this, and I'll tell you more about this later. But this is a very strong argument pointing in a direction that says something that had incredible properties had to initiate this thing. And isn't it amazing that it's almost exactly like the God that we have traditionally talked about?
Amen.
Wow.
And certainly the God of the Bible fits into this. Right? So, in the beginning, how do different physicists and cosmologists and astrophysicists respond to this? Maybe you know Stephen Hawking. One of the things, he's an atheist, by the way, was an atheist. He died recently, not too long ago. The Big Bang clearly has religious implications. He's an atheist, but he admits that. But he's not the only one. So here's Arthur Eddington. He was the guy who proved that stars move when they're traveling. Their light travels through a gravitational field. The first person to verify experimentally that Einstein's general theory of relativity was correct. He says the beginning of the universe seems to present insuperable difficulties unless we agree to look on it as frankly supernatural. And he was he was the guy who used the word repulsive. He did not want there to be a beginning. He said it's repulsive, but yet, I don't know, you pin him down and he says, frankly, it's supernatural. Right? What are these guys doing? All right. So, and I could go on and on and on. There's plenty of scientists who have these, and I'll show you a couple more later on. But that's a cosmological argument. That's the idea that everything that it, came into being had to have a cause to initiate. Whatever that cause was that kicked off the universe had to have extremely special properties, unlike anything we've ever seen. And those properties are very similar to God. All right, now, this is the teleological argument. So teleology means the study of purposes, okay? So now, we're going to talk about the laws of physics and how they fit in just a special way to allow life, as if they're designed to allow life, okay? So our universe has different laws of physics. So one of these laws is just gravity, that things are attracted toward the Earth. Another one would be laws of electromagnetic properties. This is Maxwell's equations that we talked about before. Now, here's the question. What if we change the rules a little bit? What if we made them slightly different? Okay? And you might think, well, if I changed, would we just look different? Would we now have life where things have two heads instead of one? I have a little picture of a frog here that has two heads. Okay, so if we change the rules of physics, would we just have two heads? Would we look different, but there'd still be life? Or if I change the rules of physics a little bit, would it lead to no life at all? What I'm going to tell you is it's almost always this and almost never that. The window for life is extremely narrow. And I'll just talk with you about a couple of these things. Okay, in order for life to exist, many laws and constants must be perfectly aligned. Most combinations don't work. So let's do a few examples. So here, this is a little bit like what happens if you're playing cards. So I'm going to talk about probabilities and cards. So let me just sort of get you ready for that. One way to get ready for it is to think of this. Say you're playing a game of poker with some friends, and you're dealing what you think is a normal deck, and you deal it to your friend. You're betting, I don't know, your lunch money, something like that. So you want to win, right? And there's also pride on the line. And so your friend gets this, okay? So they get this hand dealt from the deck. Well, that's a pretty good hand. I don't think much can beat it, right? Okay? And then you go, okay, you get the money this round. Next round I'm gonna get you. And then the next time he plays, he gets this again. And then the next time he plays, he gets it again. And you play 100 hands, and all night long, he gets the same thing again and again and again. What do you think is going on? There's cheating. There's no way. This is not random. You got the idea. It's not random. Somebody's messing with it. That's the whole argument about what I'm going to tell you. I'm going to tell you that we're going to look at the odds of these constants being set up in such a way. The odds of this are worse than this. Okay? So let's go into one of these. So gravity. So we know gravity brings things down. But here, we just talked about the Big Bang. So let me tell you what I'm going to say about gravity. The Big Bang, everything expands from that little beach ball all the way out. But the force and the speed with which it went out had to be just right. If it went too fast, what would happen is all matter would be spread out so thin that you'd never get two hydrogen molecules coming together. And so you'd never get clumps of gas forming stars. If it blew out too hard, you get no star formation. You just get vapor. Okay? On the other hand, if it blew out not hard enough, what would happen? Gravity would pull it all back and it'd come back into the beach ball. Okay? So now here's the question. I mean, what's the window for the strength of that thing, right? You don't want to be too strong, you don't want to be too weak. How narrow do I have to get it to be just right so that things expand and you still get star formation? How narrow is that window? Well, let's talk about it here. So, if the rate of expansion had been greater than even 1 part in a million, stars and planets would not have been able to form. So if it went out too fast, 1 part in a million, it wouldn't have been able to form. If the rate of expansion 1 second after the Big Bang had been smaller by 1 part in 100,000 million, the universe would have recollapsed before it ever reached its present size. That's Stephen Hawking, an atheist. Okay, so let's just think about this. 1 part in 100,000 million. So 100,000 is 10 to the 6, million is 10 to the 9th, 10 to the 9th. So that's, 10 to the 28th. The 10 to the 28th power, okay? That's 1 in 10 to the 28th, something like that. It's on that order, right? That's really, really, really rare. But what I'm going to tell you is that's not even the worst thing, okay? It's not even the worst. So let's do another one here. The electromagnetic force. So we have positive charges and negative charges. They attract each other, okay? And we have to have just the right number of these particles. So the number of positively charged particles perfectly balances the number of negatively charged. Why? This might sound like it's normal or who cares, whatever. It turns out that if there was even a very, very slight imbalance, I'm going to show you the numbers here in a second, you would not have things working as well. Okay, why would that be? Because what would happen is if they weren't perfectly balanced, if I had, let's say, more negative charge than positive, let's say all of us had like some net excess positive charge, what would happen? We would repel each other. All matter would repel itself. So if I had a bunch of dust and all that dust was positively charged, what it would do is it would spread out, fall away. Just like if you take two ends of a magnet that repel each other, they move away. It's the electromagnetic force. So it pushes apart. You have to have just the right amount of positively charged stuff and negatively charged stuff. If it's not perfectly balanced, everything would again fly apart rapidly. Okay? If one type of particle outnumbered the other by this little part in 10 to the 40th, this is even worse. Okay, it goes from 10 to 28, something like that, to 10 to the 40th. So this is getting worse, but wait, it gets even worse. All right, and these facts that I'm listing here are not under dispute. Everybody agrees on this who studies it. Everyone who's a cosmologist, whether they're an atheist or whether they're a theist, whether they're Christian, Muslim, or whatever, everyone who knows this material says that's absolutely true. Okay, so what about this? The matter-antimatter imbalance is just right. So here it is, it's not balanced, okay? So if it were perfectly balanced, what would happen? Matter and antimatter, if you've ever watched Star Trek, if these two things come together, they annihilate. And people do this all the time in particle physics. If you have a negative electron and you have a positively charged electron, that's antimatter. These things, it's called a positron. If these things come together, they annihilate and release energy. So when the universe started, there was matter and there was antimatter. And there was gobs of it, huge amounts of it, right? What happens is they were just slightly out of balance by a very, very, very tiny amount. And what that meant is that all this antimatter took over all that matter and left a little bit of matter around, and that's what we are. We're the remnant of it. A tiny, tiny sliver of a remainder. That's what constitutes all the mass of the universe. If they had been perfectly balanced, nothing would have worked, okay? And so the numbers on this, I give you this link here, I'll give you the slides later, but it's very, very bad, okay? It's extremely bad. Here's one more thing. There's this thing called the entropy of the universe. And let me explain a little bit what that is. So entropy is disorder, okay? And normally when you have a bomb blow up, it's highly disordered. And the stuff that flies out is just random junk, right? So if something explodes and you just see junk all over it, okay? But when the Big Bang happened, we didn't see just junk. We saw planets, we saw stars, we saw us. Okay? So in order to have structure come from an explosion, you have to have everything extremely ordered at the beginning. And they've been able to do calculations about what that order had to be. And so this guy, Roger Penrose, who just won a Nobel Prize in the last 2 years, he was a protege of Hawking. He did work with Hawking. And one of the things that he said is that this entropy, and I've got the link on YouTube and you can go to it and look at it, and he's not a theist, but he says the entropy had to be smaller. He says all this stuff that I'm telling you about right now is chicken feed compared to what I'm about to tell you. He says the entropy had to be so low, in other words, things had to be so ordered, that it was more rare than 10 raised to the power 10 raised to the power 120. Okay? That is beyond our calculation. Okay? And this is Penrose, and he's someone who doesn't believe in a God, although, you know, if you corner him and start pushing, he's like, well, I can understand why people might think that. Okay? So it's plausible to a guy like that. And so let me just kind of give you a quick illustration of something. So how hard would it be to find something that is very, very unlikely? Okay? And I wish I'd put the numbers on here, but I calculated this. So imagine we had the Sahara Desert, okay? It's not all sand, but you know, there's cities in here and other things like that. I'm sure there's picnic tables or whatever. But imagine there's lots of sand in here, okay? Now what we do is we go into the entire Sahara Desert, we pick out one grain of sand, and we paint it blue. We throw it back in, and we mix it up because we've got a giant mixer because we're connected to God. And he can do this kind of stuff. And now he says, go in and pick one. Just pick one. And if you went in and you picked that blue grain of sand on your very first try, that still wouldn't be anywhere near as unlikely as 10 to the 10 to the 120. And remember, that's just the entropy, right? Then we got to talk about gravity. Then we got to talk about electric charge. Then we got to talk about matter and antimatter. And you know what? I've only scratched the surface. You know how many of these little situations there are? There's like 15 to 18 to 20, depending on who you talk to. Okay? They're about, I'm being conservative here. There's 15 physical constants that have to be just right. All right? If any one of these varied by even a small amount, we would not get star formation. Okay, now it might be perhaps that you could have life if you didn't have a star. Right now, we don't know how that could happen. And stars are the energy source of the universe. You take hydrogen, gravity pushes it together, they fuse, they release energy. This is like the giant motor of the universe. If you don't have energy pumping into stuff, you can't have matter then self-organize into more and more complexity. You wouldn't get life. You'd have to have energy from some other source. Okay, everybody agrees on this stuff that I just told you. Okay? Nobody doubts what I just said. All of that is ironclad science. It's not some person's opinion. You can look it all up. I can give you all the papers. Nobody disputes it. But now what happens? How do they interpret it? I've had lots of fun conversations with people. Okay, let me just show you a couple more articles. This is an article by Martin Rees. He's the royal astronomer. He wrote this a long time ago, 1979. Basic features of stars, galaxies, planets, everyday world are essentially determined by a few metaphysical, microphysical constants and by the effects of gravitation. Many interrelations between different scales at first sight seem surprising and straightforward consequences of simple physical arguments. But several aspects of our universe, some of which seem to be prerequisites for the evolution of any form of life, depend rather delicately, oh my, how understated you are, and on apparent coincidences among physical constants. This is a guy who doesn't believe in a God, but he's trying to be very, conservative in how he states it, right? This is another paper. Here they talk about 18 arbitrary parameters in the standard model in your everyday life. These also have to be very finely tuned, really finely tuned. And then I teach this physics course, and I looked at the back of our textbook. The guy who writes it, as far as I know, doesn't believe in God. But he's obligated to say something because the situation is so stinking incredible, right? So what does he say? The questions raised by cosmology are difficult and profound and may seem removed from everyday reality. We can always say the sun is shining, it's going to shine on for an unimaginably long time, all is well. Nonetheless, questions of cosmology are deep ones that fascinate the human intellect. One aspect that is especially intriguing is this. Calculations of the formation and evolution of the universe have been performed that deliberately vary the values, just slightly, of certain fundamental physical constants. The result, a universe in which life as we know it could not exist. For example, if the difference in the mass between a proton and electron were zero or less than the mass of the electron, there would be no atoms. Electrons would be captured by protons and neutrons. So you never have chemicals. You wouldn't have atoms that have electrons that would bond with, right? So Such results have contributed to a philosophical idea called the anthropic principle. So, something that leads to anthropos, or people, or humans, which says that if the universe were even a little different than it is, we could not be here. We physicists are trying to find out if there are some undiscovered fundamental laws that determine those conditions that allowed us to exist. A poet might say that the universe is exquisitely tuned, almost as if to accommodate us. You can feel him squirming in his chair. He hates to admit it, but admit it, he does. And every single scientist, if you corner them on it and they know the facts, they go, yeah, okay, all right, all right. And I had a conversation. Yeah, okay, so there's a guy named John Mather who won a Nobel Prize for the cosmic microwave background radiation exploration satellite. So he looked at, so after the Big Bang, there was an echo. We were able to pick it up with a satellite. So he won it for his work on that, along with another guy named Sweet. He came to our department and talked to him. And so I was able to go up and talk to him privately. And I said, well, hey, what do you think about the cosmological constant you described? So this is something that has been said to be correct precisely by 1 part in 10 to the 100. Not 10 to the 10 to the 120, 10 to the 100. And I said, what do you think about that? Huh? I didn't say, huh. That's what I was feeling inside. So I said, what do you think about that? And here's what he said to me. He goes, yeah, you're right. It's really precise. So what? What do you want me to do with that? Now, he didn't say it in exactly that tone, but he said, what do you want me to do with that? It's not a scientific question. I can't say anything more about it. I can't do an experiment on it. So I leave it. He was a little irritated. He wasn't as irritated as I'm saying. I'm overplaying it. Sorry. But anyway, and I talked with another guy. I don't know if you've heard this, the LIGO, which does basically, they collect gravitational waves. So they're looking at like 2 black holes that merge, and when they merge, they set off a ripple in space-time. Now they have these laser interferometers that pick up these ripples. And they can say, oh, wow, we got the wave from that event. We can see what it was. And I talked with one of these guys. This is a few years before they hit it big. And I said, what do you think about the fine-tuning of the universe? And he's like, so what? What do you want me to say? Not science. They get irritated and they walk away from it. There's another guy in our department who won a Rhodes Scholarship. He's a nuclear theorist, really smart guy. I said, hey, what do you think about this? He's like, have one. He just didn't want to talk about it. He didn't want to talk about it at all. There was yet another guy that I talked to. He's a cosmologist. He said, well, a high energy physicist who does theory that touches on cosmology. I said, so Mike, what do you think about this? I mean, whatever had to start this whole thing and keep it going and have it just fine-tuned, I mean, what was that agent? He goes, well, I guess it had to be something that was, it had to be powerful, right? He said, yeah, it had to be powerful. Said, well, it had to be in favor of light. It had to be outside of time. It had to be immaterial. He's like, yeah, it had a lot of interesting properties. I'm like, but what do you think? No. And so, a lot of people, when they see this kind of thing, they go, well, why are all these people who are atheists saying these things, and why do they not then become theists? And to that, let me just ask you this. Do we have enough scientific evidence that smoking is bad? We do. Why then are there still people who smoke? They like it. They want to keep doing it. They find it hard to give up. Why does somebody not embrace the idea of God once you've seen this? They might be scared, they might not want to. So my only point is just this. The humans are complex, right? We don't always go with the evidence. Sometimes we go with what we feel comfortable. Sometimes we don't want to hear the evidence. Sometimes we don't want to look at it. But the evidence is overwhelming in favor of something outside of time causing all this, that's powerful, that's omnipotent, that's beneficial to life. Okay, so there's another argument that people will give, and I just want to address this briefly. What they say is this: there's this thing called the multiverse. So there's something called string theory, and string theory has lots and lots of possible solutions, and each solution basically could lead to a different type of universe in which the laws of physics would be slightly different. And in almost all of those universes, there would be no life at all. And what people say is, well, probably there's trillions and zillions of universes, and there's no life in any of them. We just happen to be in the one where there is life. And that's why we're talking about it. In other words, we're just lucky. We happen to be in the one universe. But they say that there's a whole bunch of these other ones out there. Oh, and by the way, if it's an alternate universe, we don't have a way of getting there. We have no way of knowing whether it's there, at least not yet. We have no way. So this is something for which you can't get proof, and you might not even ever be able to get proof. And so if you want to hold on to it, you have to do so by faith. Okay? Yeah. So here's an analogy given by a philosopher named John Wesley. He said, what would happen if you were supposed to be executed, and there were 10 trained snipers, this is his argument, and 10 trained snipers who were all aiming at you, and they all were really expert marksmen, and they shoot all at the same time, and they all miss. What would you think? A little bit like the multiple royal flushes again and again and again. Would you think that you just got lucky? Or would you think that maybe something's up? And what John Leslie's point is that when things get so improbable, it's completely reasonable to think that something outside of chance is operating. In fact, that's the whole scientific method. You basically run an experiment and you say, what are the odds that it turned out this way? And if it's more rare than 1 in 20, typically that's the scientific level. We go, okay, we'll accept this as being probably not due to chance. That means there's some causative factor that we haven't identified yet. 1 in 20 is enough to get your paper published in Science, not 1/10 to the 120, right? 1 in 20 is enough for Science. Why do they balk at this? Maybe because they want to keep smoking. What are they smoking? All right, so here's the teleological argument, just to kind of sum it up. The fine-tuning of the universe is due to either chance, necessity, or design. So either we're really, really lucky, or it had to be that way, or some causative agent made it that way. It is not due to chance or necessity. It does not have to be that way. I could go into that argument. We didn't really touch on it here. But it's definitely not due to chance. Therefore, it's due to design. Something designs it. Okay, here's a couple more quotes. So this is Fred Hoyle, the guy who did not believe in God and was the steady state guy. A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question. His own words, right? So crazy. Here's David Deutsch. Many credit him with basically the kickoff of quantum computation. If anyone claims not to be surprised by the special features of the universe he is hiding his head in the sand. These special features are surprisingly unlikely. Another atheist, by the way. Okay. And one more. Oh, now he's not talking about the Big Bang, but he's talking about the tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. He admits it too. All right, so what do we conclude? All right. So whatever created the universe is powerful and exists outside of space and time. We talked about that. Whatever established the laws of the universe favors life and is very intelligent. And then this whatever is God. This is a completely reasonable conclusion. Something that is omnipotent, something that's eternal, omnipresent, loving, and wise. So that's basically the argument for it. So conclusions. So who is this God, and what is this God like? When Moses wanted to talk to God and find out who he was, God gave him his name. And his name in Exodus 3:14 is this, Yahweh. But Yahweh also means in Hebrew, I am who I am. This is what you were to say to the Israelites. I am has sent me to you. I always found that extremely interesting. It's not like I was or I will be, but I am. I am. What does that mean in time? He always was, he is, and he always will be. He just is. I am. What does that mean about space? Well, I could say I am over here, but I'm not over there. That's John Beggs. I'm here, but I'm not over there. God doesn't say that. God says, I am here, there, and everywhere. Dr. Seuss kind of way, right? So he's everywhere. God is everywhere. There is no place. He's omnipresent. He's eternal, right? He has properties given just by this in the Old Testament. I am who I am. He's everywhere, and he always has been, and he always will be. And Jesus taps into this too. He plays this time game, right? So he's having an argument with some of the religious authorities, and one of the things he tells you is, very truly, I tell you, Jesus answered, before Abraham was, I am. That's weird. Yeah, bang. Wow. Right? I've always been. I am the guy who spoke from the burning bush, and now I'm before you in flesh. I have always been. I am the one who started that little beach ball. I don't know how you say beach ball either. And expanded out, right? I'm the one who led that whole thing to go. I am that God. But now here's another thing about God that I want to land on. That I am shows up in another place. God says, I am the God of your father, the God of Abraham, of Isaac, and of Jacob. He identifies himself as someone who's in relationship with people. That I am has these cosmic implications. But the most important thing is that the I am loves all of us. This I am is after you. And the whole creation was made for what? Just so we could be in relationship with him. Adam and Eve walking with God in the cool of the day. Or Peter fishing with Jesus, the Sea of Galilee. Or you praying in your bed, asking, the great I am, who always was, who always will be, and who identifies himself as your God, and the God of Katerina, and the God of Sarah, the God of Jeff, and the God of Uel. That God. That's awesome. Yeah. The whole universe is just the stage in which he wants to meet us. Let's get to know us. So that's pretty much it. Thank you. And if you guys have any questions, I'd be happy to try to field them. Yeah.